Hi. So thank you very much for having me here. And I'll move somewhere in between the scales that Richard is studying, the super distant galaxies mostly unresolved, and to where Alice was, to looking at maybe scales of 100 to 100 parsecs. Or in other words, I'll show you what happens when you take a deep dive into a single galaxy in the early universe using 40 hours of ALMA data. And this is a work that has been going on for over 5 years, involved multiple people who are either joining in or based in Leiden. I'd like to highlight John McKean, Simona Vegetti, and Jackie Hodge here. And why we want to study galaxies in the early universe becomes very evident from this plot, where basically half of all the stars in the universe were formed within the first 3 billion years after the Big Bang. And in fact, one of the main drivers of this vigorous star formation in the early universe are dusty star-forming galaxies. These are extremely star-forming objects, forming 100 to 1,000 times more stars than the Milky Way per year. And they are a real challenge into theoretical models of galaxy evolution. And we do see that they seem to be quite different environments from what we see in the present day. They seem to have highly turbulent interstellar medium, and there are indications that they have a very top-heavy IMF. So there seems to be something quite distinct happening in them in terms of how star formation is triggered, how it proceeds, and how it's regulated. And so the question I'm after is, if you are a newborn star, what difference will it make for you to be born in the Orion Nebula today and in one of these dusty star-forming galaxies 10 giga-years ago? And the answer to this question is intimately linked to the properties of the molecular clouds from which stars form, such as the gas density, temperature, the UV radiation, effects of supermassive black holes in the central regions, or shocks from supernovae. And indeed, the ISM of these high redshift sources have been extensively studied using a number of facilities, but the main limitation of many of these studies is that they look at unresolved or marginally resolved observations. And when you try to infer using radiative transfer modeling the underlying physical conditions, you do it for some galaxy average values. Now, the thing we know when we look at any nearby galaxy, especially the star-forming ones, they are very far from uniform. So if you do this in the unresolved sense, you are probably mixing some extended quiescent gas with very compact, dense star-forming regions. And also in this unresolved approach, one of the assumptions we have to make is that all the different emission lines we are looking at, C plus, CO, dust continuum, are co-spatial, which is not necessarily the case. And so really what we want to do is to probe down to the scales of 100 parsecs and below to look at the very size of star formation. 100 parsecs at high redshift is about 10 to 20 milliarc seconds. That's very much on the boundary of ALMA can do, if not beyond. So a way how to get around this is to look at strongly lensed objects, and I'll be talking about one of these, SDP81, seen here in beautiful ALMA long baseline campaign imaging. And I would argue that SDP81 is really the best studied dusty star-forming galaxy that we know. It was found by Herschel in the Age Atlas survey, but crucially it was selected as one of the targets of the ALMA long baseline campaign in the autumn of 2014, which is the first time ALMA went out all the way to the 13-kilometer baselines. And back then, the ALMA team obtained 4 to 6 hours on source in 3 different bands, which was amazing amount of high-resolution data. And this is not where the work stopped. I'll be talking today about adding ALMA band 3 and band observations. And there's also extensive data from VLA, whether it's CO1 to 0 or recent observations of dense gas tracers and radius continuum. And altogether, we have about 40 hours of ALMA data and 150 hours on the VLA on this single galaxy, which is also strongly lensed. Now, how do we go from beautiful arches like this to how our galaxy actually looks like? To do this, we have to use the so-called lens modeling, which means we have to model both the mass distribution of the lensing galaxy or the lensing cluster and the surface brightness distribution of the background source. And we probably all know the cleaning algorithm that makes our beautiful interferometric images, but this has some downsides when you try to do lens modeling. So during my PhD, I modified one of the codes developed originally for optical data by Vegeti and Koopmans to work directly in the UV plane by modeling the visibilities directly. And it uses adaptive grid to reconstruct the background source with high fidelity. And there's a lot of development going on in this area still. So how does SDP81 look like when we do all this magic? So here is the continuum data. You see band 6, band 7, band 8 continuum. I would like to highlight that the resolution does vary across the source, but the median resolution we achieve is about 200 parsecs. It's about 25 milliarc seconds, really on the edge of what you could do with ALMA. And you see that the continuum has these 2 to 3 bright clumps and doesn't change very much from band to band. That's roughly what we would expect. What does change are when you look at CO lines. So here we have CO32, kind of smooth because the signal to noise ratio wasn't great. So we miss some of the detailed structure. But when you look at 5 to 4, you see it sort of follows the continuum data, except it's extended into this cross region. I hope you can see my mouse. Yes, good. And but when you move to CO8 to 7 and 10 to 9, they are progressively more concentrated to the north of the source. So what you see immediately is that there is some strong variation in CO excitation on kiloparsec scales. And this source is really far from being completely uniform. And then the C2 is doing its own thing. It's sort of tracing the far infrared continuum, but being more puffy. And then it again extends into this region at high signal to noise ratio. The data is all publicly available. So if you want to have a look at them, try radiative transfer code on them, please go ahead. And when you mesh this all together, here is maybe a nicer overview of how just how different the far infrared continuum, the CO and C2 emissions are distributed. And you can see that the C2 seems to go off the screen over here, and off the screen it goes. We see a long, potentially tidal tail over 10 kiloparsecs long. And this is the previous figure I was showing. Basically, there's this very compact far infrared continuum. And then half of the C2 emission is completely unassociated with where the far infrared is coming from. And this again highlights the dangers of trying to infer the physical conditions in these galaxies from unresolved data. Now, when we have 4 CO lines, C2 and far infrared, mapped across the source, we can try to use radiative transfer modeling to infer the physical conditions across the source. I'm using the PDR toolbox models. We downsample the data onto 200 by 200 parsec pixels. And this is what you get. On top is the far UV field map. The contours are far infrared continuum. And you see that the far UV field peaks where the continuum peaks, which is maybe what you would expect. Then it drops down in this region where we see mostly only CO and C2 emission, no far infrared. The gas density is more uniform across the source, at least given the data we have, with some concentration in the north. And I believe this is really the first time we have such a high resolution view of one of these distant galaxies. So that was very exciting to see this. To put this into context, here is where our data fall down in the far UV radiation versus gas density. Sorry, should have been log scale. So here is where our data is compared to previous unresolved observations of different dusty star-forming galaxies, seen in pink. So we see once we resolve them, we move to a bit more extreme values. And because we are probing such small scales, for higher redshift at least, I decided to overplot measurements for different star-forming regions in the local group. And to press this analogy a bit further, I decided to go back to the Orion, and here is the Trapezium nebula in Orion, which was studied by Goico Achea a few years ago using very much the same set of lines and PDR modeling tools as we did. And what they found is that the inner region Trapezium falls somewhere over here in this parameter space. The outer region falls somewhere over here. And we see that the SDP81 is quite extreme even compared to the Trapezium. And we are still looking at ISM average over 200 parsec scales. So there are some true monsters hiding underneath our data. And we are not done yet, because lensing not only gives you magnification or high resolution, also allows you to see much fainter lines, which can still provide critical insights into what's happening in this galaxy. So with my student Joshiwa van Marrewijk, we were looking at HC and HCO+, two dense gas tracers in this galaxy, using a range of, using both image plane and UV plane analysis. And we have a pretty nice HCO plus 423 detection. There's no sign of HCN 423, which is actually very interesting. And we are now going over our new VLA data, looking at the ground state transitions of these two tracers. And just to finish my final minute of my talk, this is still not the end of the story. There is much more stuff coming in. We now have much better CO322 data. So this is what we did our work on. This is what we have now. For curiosity, this data was recovered from ALMA QA2 rejected data, which we got the raw visibilities for and processed them manually, and suddenly have a very nice data set. With Steven Surgeon, we put in a JWST mid-size proposal to look at a whole slew of emission lines in the source, H-alpha, Paschen alpha lines, pHs. And with Divergent van der Vlucht and Hiddo Algera, we very recently got observations of the radio synchrotron and free emission in the source at high resolution. And by very recently, I think the observations finished literally last week. So there's much more data to come, and I'll stop here. Thank you very much.